primary reason for restricting additional levels of ground fault protection, or GFP, on hospital emergency electrical systems is to guarantee a dependable power supply during critical situations. Additional ground fault protection devices can elevate the risk of unwanted tripping, particularly during transient voltage surges or other disturbances capable of generating false ground faults. This could disrupt vital medical equipment and jeopardize patient lives. Adding multiple levels of ground fault protection can result in coordination issues, where devices trip in incorrect sequences or at excessively low fault currents. This may trigger a cascading effect, disrupting the entire emergency system. Each ground fault protection device added to the system constitutes a potential point of failure. With multiple devices, the likelihood of system unavailability increases, which is unacceptable in a medical environment where continuous power supply is paramount. The 2008 National Electrical Code, or NEC 517.17, does not explicitly prohibit the installation of any ground fault protection on hospital emergency electrical systems. However, it is generally deemed unnecessary and potentially detrimental. The wiring and equipment employed in hospital emergency systems are typically of high quality and subjected to rigorous testing and maintenance. Consequently, the risk of ground faults is minimal. Hospital emergency systems are typically engineered with multiple redundancy levels, encompassing redundant feeders and transfer switches. This redundancy lessens the risk of power loss due to a single ground fault. The wording additional levels in National Electrical Code 517.17 suggests that a single level of ground fault protection may be permitted. However, it is crucial to consider the intent of the code, which is to prioritize system reliability. In practice, it is exceedingly rare to see any ground fault protection on hospital emergency electrical systems. This is because the risks associated with ground fault protection outweigh the potential benefits. Instead, hospitals depend on rigorous maintenance and testing procedures to minimize the risk of ground faults and ensure continuous power supply. Let's delve further into the specific concerns related to ground fault protection in hospital emergency systems. Firstly, unnecessary tripping poses a significant threat. Ground fault protection devices are designed to detect and interrupt ground faults, which are unintentional electrical paths between a live conductor and ground. However, these devices can sometimes trip falsely due to transient voltage surges, electromagnetic interference, or other electrical disturbances. In a hospital setting, where critical medical equipment relies on a stable power supply, even a momentary interruption can have serious consequences. Secondly, impaired coordination can arise when multiple ground fault protection devices are installed in series. Coordination refers to the selective tripping of protective devices, where the device closest to the fault is the one that trips, while upstream devices remain operational. This prevents widespread power outages and ensures that only the affected portion of the system is de-energized. However, achieving proper coordination with multiple ground fault protection devices can be challenging, especially in complex electrical systems. If the devices are not properly coordinated, a fault in one area could cause multiple devices to trip, leading to a larger power outage than necessary. Thirdly, reduced availability is a concern because each ground fault protection device represents a potential point of failure. Like any electrical component, ground fault protection devices can fail due to age, wear and tear, or manufacturing defects. If a ground fault protection device fails, it could either trip unnecessarily, causing a power outage, or fail to trip where ground fault occurs, leaving the system unprotected. The more ground fault protection devices in the system, the higher the probability of a failure that could compromise the reliability of the emergency power supply. Now, let's address the question of why the National Electrical Code 517.17 doesn't explicitly forbid the installation of any ground fault protection on hospital emergency electrical systems. The rationale is that there may be specific circumstances where a single level of ground fault protection could be beneficial without significantly increasing the risk of unnecessary tripping, impaired coordination, or reduced availability. For instance, a single ground fault protection device might be installed on the main feeder to the emergency system to protect against ground faults that could occur upstream of the transfer switches. However, such installations are rare and require careful engineering analysis to ensure that the ground fault protection device is properly coordinated with other protective devices in the system and that it does not compromise the overall reliability of the emergency power supply. In most cases, hospitals rely on other methods to minimize the risk of ground faults and ensure continuous power supply. These methods include rigorous maintenance and testing procedures, the use of high-quality wiring and equipment, and the implementation of redundant power systems. Regular inspections and testing can help to identify and correct potential problems before they lead to ground faults. High-quality wiring and equipment are less likely to develop insulation failures or other defects that could cause ground faults. Redundant power systems, such as multiple feeders and transfer switches, can provide backup power in the event of a ground fault or other electrical failure. The National Electrical Code provides specific requirements for the design and installation of electrical systems in healthcare facilities, including hospitals. These requirements are intended to minimize the risk of electrical hazards and ensure a safe and reliable power supply for medical equipment and patient care areas. The code addresses a wide range of topics, including wiring methods, overcurrent protection, grounding, and emergency power systems. It is important for electrical engineers and contractors working in hospitals to be thoroughly familiar with the requirements of the National Electrical Code and to follow them carefully. In addition to the National Electrical Code, hospitals may also be subject to other regulations and standards related to electrical safety and power reliability. For example, the Joint Commission, which accredits hospitals in the United States, has specific requirements for emergency power systems. These requirements address topics such as generator testing, maintenance, and fuel supply. Hospitals may also have their own internal policies and procedures for electrical safety and power reliability. These policies and procedures should be based on industry best practices and tailored to the specific needs of the hospital. Effective electrical safety and power reliability programs require the involvement of a wide range of personnel, including electrical engineers, maintenance technicians, facility managers, and clinical staff. All personnel should be properly trained on electrical safety procedures and be aware of the potential hazards associated with electrical equipment. Regular training and drills can help to ensure that personnel are prepared to respond effectively in the event of an electrical emergency. The implementation of a comprehensive electrical safety and power reliability program can help hospitals to minimize the risk of electrical hazards, ensure a continuous power supply for critical medical equipment, and protect the safety of patients and staff. Ground fault protection devices are an important component of electrical safety systems, but they must be properly selected, installed, and maintained to be effective. In hospital emergency systems, the risks associated with additional levels of ground fault protection generally outweigh the potential benefits. Therefore, hospitals typically rely on other methods to minimize the risk of ground faults and ensure continuous power supply. These methods include rigorous maintenance and testing procedures, the use of high-quality wiring and equipment, and the implementation of redundant power systems. The goal is to create a robust and reliable electrical system that can meet the critical needs of the hospital, prioritizing patient safety. The decision of whether or not to install ground fault protection on a hospital emergency system should be made on a case-by-case basis, taking into account the specific characteristics of the system and the potential risks and benefits. A thorough engineering analysis should be performed to ensure that any ground fault protection devices are properly coordinated and do not compromise the overall reliability of the emergency power supply. Ground fault protection is a crucial aspect of electrical safety, but its application in hospital emergency systems requires careful consideration to ensure the reliable delivery of power to critical life support equipment. Understanding the nuances of the National Electrical Code and the potential risks associated with ground fault protection is essential for electrical professionals working in healthcare facilities. Ultimately, the goal is to create a safe and reliable electrical environment that supports the delivery of high-quality patient care. It is important to remember that electrical systems in hospitals are complex and require specialized knowledge and expertise. Hospitals should engage qualified electrical engineers and contractors to design, install, and maintain their electrical systems. Regular inspections and testing should be performed to identify and correct potential problems before they lead to electrical hazards. By following these best practices, hospitals can minimize the risk of electrical accidents and ensure the safety of patients, staff, and visitors. Furthermore, technological advancements in electrical equipment and monitoring systems are constantly evolving, offering new opportunities to enhance safety and reliability in hospital settings. Staying informed about these advancements and incorporating them into electrical system designs and maintenance practices can further improve the performance of electrical systems. The focus on safety and reliability within hospitals extends beyond electrical systems and permeates all aspects of facility operations. A holistic approach to safety is essential for creating a secure and supportive environment for patients, staff, and visitors. This includes implementing comprehensive safety protocols, providing ongoing training for personnel, and fostering a culture of safety awareness throughout the organization. By prioritizing safety in all aspects of operations, hospitals can minimize risks, prevent accidents, and ensure the well-being of everyone within the facility. The electrical system is a vital component of a hospital's infrastructure, and its safety and reliability are paramount. By understanding the potential hazards associated with electrical systems, following the requirements of the National Electrical Code, and implementing best practices for maintenance and testing, hospitals can create a safe and reliable electrical environment that supports the delivery of high-quality patient care. The coordination between electrical engineers, maintenance personnel, and hospital staff is critical for ensuring the ongoing safety and reliability of electrical systems. Regular communication and collaboration can help to identify and address potential problems before they escalate into major issues. A proactive approach to electrical safety is essential for preventing accidents and ensuring the well-being of everyone in the hospital. In addition to the technical aspects of electrical safety, it is also important to consider the human factors. Human error can contribute to electrical accidents, so it is essential to provide adequate training and supervision for personnel who work with electrical equipment. Personnel should be trained to recognize potential hazards, follow safety procedures, and use personal protective equipment properly. A strong safety culture can help to reduce the risk of human error and create a safer working environment. Continuous monitoring of electrical systems can help to identify potential problems early on. Advanced monitoring systems can detect anomalies in voltage, current, and other parameters that may indicate a developing fault. These systems can also provide alerts when equipment is operating outside of its normal range. By monitoring electrical systems continuously, hospitals can identify and address potential problems before they lead to major outages or accidents. Finally, it is important to remember that electrical safety is an ongoing process. Electrical systems should be regularly inspected, tested, and maintained to ensure that they are operating safely and reliably. As technology advances and new electrical equipment is introduced, hospitals should update their safety protocols and training programs accordingly. By committing to continuous improvement in electrical safety, hospitals can create a safer environment for patients, staff, and visitors. Electrical safety in hospitals is a shared responsibility. Everyone who works in a hospital has a role to play in ensuring that the electrical system is safe and reliable. By working together, electrical engineers, maintenance personnel, hospital staff, and patients can create a safer and healthier environment for all.